All right, now I'd like to transition to talking about what are we going to do with all this stuff. What kind of problems are we actually going to be solving? Modeling with exponentials and logs. So section 4.6 is modeling with exponentials and logs. And I even have a brief, I have a little bit of data from coronavirus in San Mateo County that will relate to this. Okay, so these are the objectives of this section, of section 4.6, to talk about exponential growth and doubling time, to talk about exponential growth in terms of relative growth rate, which is usually like percentage rate of change, and to talk about radioactive decay and half-life. Okay, and we'll even introduce this thing that's kind of cool called Newton's law of cooling. I can't remember if it's in any of the homework, okay? But this is really kind of like the conclusion of chapter 4, which is where we actually use the exponentials and logs for some real-ish stuff, okay? So the thing about this is that many processes that occur in nature, such as population growth, radioactive decay, heat diffusion, like spread of heat, and numerous others, like the early onset of a pandemic, can be modeled by using exponential functions. Right? And remember, exponential functions, we can write them either as y equals a times b to the x. We can write them as y equals a times e to the kx. And then we have that other compound interest form. But pretty much we're going to deal with these two as models, right? And in particular, we're going to focus on getting comfortable with this form because it's good for calculus and science, okay? Okay. And lots of other things. So let's look at the examples for doubling time, okay? How many bio majors in here? Any bio majors in the house? Say what's up. Cool. Well, suppose we start with a single bacterium. And what happens in a petri dishes actually have like food for bacteria, which is basically like Jello, but it's like a sterile Jello. So like in the Jello, the bacteria gets food. You know, kind of like bacteria on like your lunch meat or whatever. It wants to eat, the bacteria eats the sugar and the protein on there, and then it divides and it grows, right? And they're saying that this bacteria divides every hour, which means that each cell, right? So if I have here's like my bacteria cell, it's going to split into two, and you're going to have two after every hour. So I went from 1 to 2, and then what happens after the next hour? I have 1, 2. If both of these doesn't divide, now I'll have 3, 4 of them, right? And you can see that as you go along, every time you're going to double, right? So 1, you're going to multiply by 2. All of them divide in half, and you get twice as many as you had before, right? So in the next hour, so here's this is hour 0, this is hour 1, this is hour 2, this is in hour 3, right? You would have 8 bacteria, and hour 4 you'd have 16, and so on. Okay, so if you made a little table of T's and the number of bacteria, F of T, it'd be 0 is 2, no, sorry, 0 is 1, 0 is 1, 1 is 2, 2 is 4, 3 is 8, 4 is 16, and this is precisely the doubling function, 2 to the T power, right? So at T hours later, you have 2 to the T bacteria remaining, okay? So if you start with 10, for example, 10 of these bacteria, then the population is modeled by this thing right here, okay? Where you have f of t is equal to 10 times 2 to the t, so that your table has an initial value, right? So 2 is going to be the initial value. And this is going to be doubles every hour. And because t is in units of hours, that means it doubles every hour, right? So in general, though, okay, in general, though, not everything doubles every hour, but we can sort of write things in this doubling time form, which is essentially a new exponential form where we're going to double every a. And so I'll try to explain to you why this is doubling every a. But so, for example, a slower growing strain of bacteria doubles every 3 hours. Okay, so let's look at that. If I have t, okay, and I start with 10. So at times 0, there's 10. Okay, and here's my f of t, and I say it doubles every 3 hours. Okay, doubling every 3 hours. If I say doubles every 3 hours, okay, 0, 1, 2, 3. How many will I have after 3 hours?
$270.
Nope. Doubles every 3 hours. So in
20.
3 hours, I'm going to multiply it by 2.
I mean 20.
Thank you. Okay.
My mistake.
Oh, that's cool. Right. So what about in 6 hours? The next 3 hours, we're going to multiply by 2. And so after 6 hours, there will be 40. Okay. So how do we find the actual model here? What we can do is we can say, well, we know that this looks like y equals a times b to the t. We know that it's in this form, okay? So basically, I want to show you, I want to convince you that b is equal 2 to the 1/3 power, okay? So if I have y is equal to a b to the t, I know that from this point, the initial value is 10, so y is equal to 10 times b to the t, okay? Then let's pick this point. I know that when I have 20, 10 times b to the 3 has to give me 20, okay? So now I want you to solve for b. What would b be? It's going to be 10. You divide both sides by 10. Divide both sides by 10. You get 2 is equal to b cubed, okay? Now what are you going to do? In order to isolate b, you take the third root of both sides. Okay, and that would cancel this 3 out over here, and I would get that 2 to the 1/3 power is what the base must be for this equation, for this function. Okay, so I get this. So I get that f of t is equal to 10 times 2 to the 1/3 power to the t. And remember, I can multiply these two powers, and so I get 10 times 2 to the 1/3 times t, which is exactly this. So I'm sorry, this is not well organized writing. 10 to the 2 to the t over 3. Okay, this is how we can go from this definition of doubling every 3 hours to an exponential equation to getting this form of the equation. Okay, so whenever you have doubles every 3, okay, or whenever you have doubles every a, you have a form that looks like this. Okay, let me zoom in on it, where the time variable is divided by the doubling time. Okay, A is called the doubling time, okay? Doubling time is A. You can write this exponential model in this way, okay? So let's look at this one, okay? Under ideal conditions, a certain bacteria population doubles every 3 hours. Okay. They should have changed it up. I should have changed it up. Can I change this example? Let's make it double. No, because the solution slides are there. Whatever. Nope. Doubles every 3 hours. Okay. So what do? Find a model. Okay. Find a model for the bacteria population. It's going to look like the population or the number at n of t is going to be the initial value times 2 raised to the time variable divided by a. Okay. So we're going to use that. And now I just plug in. So my function n of t is going to equal 1,000 times 2 to the t divided by 3. That's it. That's the answer to A. So if I plug in 3 hours, then this becomes 2 to the 3 over 3, or 2, and then I get 2,000. If I plug in 6, then I get 4 times that. Okay, so it works. Okay, B. Let's look at this. Notice also that t is equal to number of hours. So the time variable is in units of hours. Okay, so how do I calculate B?
Put 15 into t.
Hell yeah. T equals 15. So I'm going to do my function n of 15 is equal to 1,000 times 2 to the 15 divided by 3. Whoa, which means that it doubled 5 times. Which 2 to the 5th power. So if you do this, then it's going to be 32 followed by 3 zeros. So there's going to be 32,000 after 15 hours. Okay. So now the best part is, when will it reach 100,000? Is the question one might ask. How would we do that? Someone give me a suggestion. How do I do C? What do I do? What are we trying to solve for? They ask after how many hours. Which variable represents hours? T, right? Bacteria. Which variable represents bacteria? That's my N of T. Victoria, you're right. So what we're going to do is we're going to set N of T equal to 100,000 and solve for T. And that is where we're going to need a logarithm. Are you ready? Here's our model. Remember our model. Whoa, sorry. So our model is that starts with 1,000, doubles every 3 hours. Okay. So what am I going to do first? Divide both sides by 1,000. That's what I was going to say. And this totally cancels out, but then just 3 of these zeros cancel out. And I end up with 100 is equal to 2 to some value of t divided by 3. Oh boy, here's what we're going to do. How do we solve for t? 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 Can you hear me? Max? What are we going to do next, everybody? Shannon, Lily, Precious, what do we do next?
We do the logs.
I haven't told you what the log monster does. Okay, everybody. Once upon a time, there was a damsel trapped in an exponent tower. And she said, no. It was a helpless young prince. And he said, help me. I've never had to do anything for myself my whole life. And now I'm stuck in this tower. And there's nobody to help me. Help me. And what do we do? Well, along comes Valiant Mother Log Monster. And the log monster comes and swallows the entire thing. Okay, what happens?
You need to add the eyes.
Yeah. Okay, what does the log monster do to the exponent? Poops it out, obviously. So the log monster poops it out, and the helpless prince is, freed. So now lesson's over, but I'm going to use natural log because I like natural log better. Okay? Can we all be big kids and just be like, yeah, we don't need base 10 all the time, but we can get used to natural log because we're going to need it a lot. Okay? ln 100 equals t over 3 times ln 2. And all I did was just use that property of logarithms. Okay? So now I'm going to divide by natural log of 2. So I end up at ln 100 divided by ln of 2 is equal to t divided by 3. So my final answer is t is equal to 3 times ln of 100 divided by ln of 2. Okay? Jerry, I didn't add ln to both sides. I applied the natural log function to both sides, Precious. There was no addition involved. I know what you mean I added, like I wrote them, right? But what mathematically is occurring is that you're evaluating both sides. You're evaluating the natural log on both sides. And I told a cute story about the log monster. Really, this is what we did. First, we divided by 1,000 both sides. We take ln both sides, and that lets us bring the exponent down as multiplication, aka the log monster poops exponents. And what did we do? Then we divided by ln2 and multiply by 3. And that's how we got this answer. And what is that number? Jerry, is Jerry right? Is Jerry correct? Is it approximately 19.9316? Is that true? So in about 20 hours. Let's see if the solution slides agree with us, okay? All right, ready? It says the population is given by that. Boom. After 15 hours, we got a 32,000. For C, we set the whole thing equal to 100,000, okay? Because the model is equal to that. Now, as we go down, we divide by 1,000, take the log of each side. Ooh, look, they used common log.
It's approximately 19.93, almost 20 hours.
Bam. So we got it. And did it matter that we used log base 10? use natural log or log base 10 when we are solving equations. We just have to make sure that we get the properties right, okay? Now, are we ready to move on? I have one or two more examples. Anybody? Question? Nice. All right. Relative growth rate. Let's see. Let's see what's up with this, okay? We have used an exponential function with base 2 to model population growth in terms of the doubling time. We could also model the same population with an exponential function with base 3 in terms of tripling time. Ooh, in fact, we can find an exponential model with any base. If we use the base E, we get a population model in terms of the relative growth rate R. The rate of population growth expressed as a proportion of the population at any time. Okay. This is a trip because what it means is that when we use E, the continuously compounding thing, we can think of it as the rate at which the population is growing in terms of how big it is, okay? And when you get into calculus, the very first differential equation you're going to look at has to do with E, but basically we're going to let R equal, R is going to tell us the growth, okay, growth rate as a percentage of population size is essentially what this is, okay? So whatever the size of the population, a certain percentage of that will equal how much is about to grow, which is basically more people, more sex, more babies. And there's a direct proportionality. So let's let R be, and we call it the instantaneous growth rate. And if R is equal to 0.02, then at any time t, the growth rate is 2% of the population. That means that if we look at the population, we're going to say that about, it's going to grow by 2% in the next like hour or so, okay? In the next like moment, 2% of the population is going to be added on to the current population, okay? So when we talk about it in that way, we have this form, right? We have, it's just the same thing as p times the e to the RT. It's just continuously compound interest. But now we call it relative rate of growth, okay? So in the context of populations or natural phenomena, we call it the relative rate of growth instead of the continuously compounded rate. Okay? It's just a context thing. And in calculus, when you get into Calc 1, you will learn more about exactly why this happens, and it's really cool. Okay? But for now, we're just kind of introducing it to you, and you have to be familiar with the formulas. Okay? Now, I don't really want to read this whole slide. Can we just, okay. Let's do an example. Ready? Okay. Let's say that the initial count of a bacteria, yeah, I'm going to do it like that. Okay, the initial count of a bacteria is 500. So the initial count, we have bacteria, the initial count is 500, okay? A biologist later makes a sample count of bacteria. Oh boy, it's telling you the answer already. And it says the relative growth rate is 40%. Okay, so basically we have the initial value and the relative growth rate. We just put these things together. See the keyword relative growth rate? That tells me that it's going to look like n of t is equal to my initial value, e to the RT, right? This is the same thing as y equals a times e to the kt. It's all the same. It's not about the specific letters like n or r. It's all about the relationship between them. So e, though, is that special number 2.7. It's the natural base, okay? And so now I can just plug in r is equal to 0.4, and my initial value is 500. So my model, n of t, is going to equal 500 times e to the 0.4 times t. Okay, these are all in the exponent multiplied. Okay, so we did that one. What is the estimated count after 10 hours? Now I just have to check that my time variable is in hours. Right, so that's A. And then in B, it says it is in hours, so t is in hours. T is equal to hours. Okay, so all I'm doing here is just setting t equal to 10. Okay, so my n evaluated at 10, my counting function n is going to be 500 e to the 0.4 times 10. And that's going to be e to the 4th power. So what's 500 times e to the 4th power, everybody? For C, we're going to set n of t equal to 80,000.
For B,
Solve for t.
B, that would be 27,299.08.
So let's see, 27.
299.
Can you see my calculator? Can you see my calculator?
Yeah. We can.
Okay. I want you to all to do it times, and then notice the exponentiation function is right above the natural log, so second natural log e to the 4th. 27299. Okay. So after 10 hours, there's going to be 27,299 bacteria. Okay. Now, if we need to solve for t, here we have to set the whole thing equal to 8,000. So sorry, 80,000 in this case is going to equal my model 500 e to the 0.4 t. Okay. So now what are we going to do? Divide both sides by 500, take the natural log, divide by 0.4. That's what I was going to say. Oh. Okay. 800 divided by 5 is going to be 40. 80, wait. No. What's 800 divided by 5? It's going to be 160. Yes. I'm almost done, Marcus. So what are we going to do? Take natural log of both sides? Aha, now since I have a base e and a natural log also of the same base, I can just cancel this out. And now I get that ln of 160 is what? 0.4 times t is equal to. So I get that t is equal to ln 160 divided by 0.4. Did I do that right? Let's see, ln 160 divided by 0.4. Bam. That's about 12.69 years. Thank you, Precious. 12.6879. And that's in unit. Wait, is that years? No, that was hours. That was hours. Okay. Okay, so everybody, here is the actual solution slides. They just rounded it. So we got 500 e to the fourth power. Okay. And then we look down here. We got ln of 160 divided by 0.4, and that was 12.7. Okay. Now, everybody, do your homework. This was 4.6. Okay. Any last questions, complaints, disagreements?
I have a quick question. On Canvas, it says that we have the STEM speaker series due today. Are we still
Oh. Yeah, I'm sorry. You know what? I have to stay up late and fix all of that. Don't worry about those due dates. The STEM speaker series, whatever you can just do like a little over a page, and you just are going to watch the videos, okay? Now, when you see the STEM speaker series assignment, it should have a link to videos. Basically, it's sometime before the end of May. You have to watch. If you went to some in person already, those count. But if you didn't, then you have to watch and type up a summary response reflection. I want to keep that assignment because it's really important, I think, for you to be exposed to actual people in the STEM careers. Okay?
I just wanted to.
Yeah, I know. It's not clear because it's telling you it's due, and yet everything's all crazy. Yeah, basically there's no... If you went to one, Ashley, you can do two more by video, okay? Let me send like a clarification. I'm gonna update the assignment if it's not, and I'll send a clarification. I will also update. I will also upload today last class's notes if you want to look at the documents.
Cool. Thank you.
I'll post it, Precious. Hey, Jerry, thank you. Thank you, Jerry's. Thank you, all the people who unmuted and
I
so.
already did 4.6 homework.
What's that?
I already did homework 4.6
Well, good for you.
before this class.
For you. Is it hard?
Well, yes, it was hard, but I finished it all.
Would this class session have helped you get it done?
Yes.
Good.
Okay.
Thank
Goodbye, Mr.
you.
Goodbye, Mr. Hoffman.
Bye.
Jen, what's up, man? You got a question for me? Wait, is that Jun? Jun. Hi.
Hi.
How are you?
Good. How you doing?
Not that bad. Who is that? I can't see. I can only see the top of your face. How's class going for you?
Oh, it's good.
Yeah? You getting the homework done?
Yeah.
Okay. Cool. Well, you gonna come on Friday?
Yeah.
Okay. I'll stop harassing you. Okay. Jordy, Precious, JJ, any other questions for me? Xiaolong. Okay, bye.